Recording is rolling. It is Tuesday, January 23rd. We're going to draw ray diagrams today for mirrors, for reflective surfaces. We'll look at plane mirrors, we'll look at concave mirrors, look at convex mirrors. Right? Here's an algebra formula that goes along with the ray diagrams we're going to do today. Got some other demos for you guys. Let's do a quick recap of some of these posters. Yesterday we did all the new posters hanging around my room. Just look at the ones that are going to be relevant for today. So, law of reflection. Guys, everybody look up here. Everybody look up here. We have a mirrored surface. Then, law of reflection says, okay, relative to that mirrored surface, if you draw a normal line, so perpendicular to that surface, right, and you follow a single ray of light. Now, maybe this candle flame sending out rays of light, like a bajillion rays of light in all different directions. We're just following one ray of light, maybe like a laser light, right? It's going to bounce off the boing, so that this angle of reflection matches this angle of incidence. Boom, that's it, law of reflection, right? Now, if you have a curvy surface instead of a plane mirror, if you have a curved mirror, right, then it gets a little bit more involved. Right? Imagine if you have a mirror sphere. Right? So I have a sphere that's all mirrored surface, okay? And I'm following just one ray of light. It's kind of a boing bounce off about that direction. Right? So how can I know exactly? I can just apply the law of reflection. Here's this normal line, dashed goes straight towards the center. You can extrapolate straight towards the center, right? And then what you can show is that this reflected ray, if you extrapolate backwards, will always go through what's called a focal point. And this focal distance is always half of the radius of that sphere in this case. Okay? So the focal distance is half the radius. Okay? So now you can define how curved is some mirrored surface, some reflective surface, and then do ray diagrams. Okay? All right, we're going to do these are two of the ray diagrams you guys do today. Okay. We'll start with convex. So if you're looking at, say, the backside of a spoon, for example, or that mirrored surface, where's your image going to show up compared to the object? Okay. Look at a plane mirror. Now, you guys probably seen a plane mirror about every day, so you guys know what the answer is going to be, right? And we'll check this with this algebraic formula, right? We'll say what this says is 1 over focal distance is 1 over distance of the object plus 1 over distance of the image, right? And the fact that for these type mirrors, the object and the image are on opposite sides, right? It's called a virtual image, right? It looks like it's on the opposite side, right? Means that there's going to be negative signs involved. Now, I'm always going to call the object as being on the positive side. Therefore, these images will show up as having negative, right? Something like that. Also, these concave mirrors, that's like if you take that spoon and you turn it around. So now you're looking at the inside of a spoon, right? Or if you like, how about a cosmetic mirror? Right? So got a cosmetic mirror here, something like that. Right. Right. And I've got another example of this reflective surface called an acoustic mirror, also called a whispering dish. Let me switch my screen over and show you guys this, right? But well, you need a pair of these, right? So here's a pair of whispering dishes out in the middle of a field. Right. I know at least University of Florida has a pair of these whispering dishes in the lobby of the physics building. So if you're ever up in Gainesville, University of Florida, go to the physics building and try this out. Bring a friend with you, and then say like if your friend's standing over at one end and you're standing at the other end, right? And you whisper something so that someone beyond, say, like a meter far away, like wouldn't be able to hear you because you're just whispering it, right? But if you're standing at the focal point of one of these dishes, then that sound will all get reflected to the other whispering dish. And if your friend has their ear at the focal point of the other dish, they'll be able to hear exactly what you're saying, like as if you were standing right next to them. Okay? So yeah, that's a fun one. Yeah, so got a friend, go to Whispering Gallery. Oh yeah, Whispering Gallery. Here's a related concept. A lot of these pop up unintentionally. So a lot of like round type buildings, if they have some kind of elliptical shaped ceiling, there's a lot of legislative buildings, right, have that round type chamber, right? So a lot of state legislatures have these inadvertent whispering galleries, okay? And there's all these stories of like legislators who like spy in on their colleagues, right? So let's say someone's having some secret conversation over here about some legislative strategy. Okay? You have someone over here like spying in and hearing like as if they're talking to them, but they might be like across the room or something like that. Yeah, so there you go. Whispering dishes, acoustic mirrors. We got these concave mirrors, right? And so let's do the ray diagrams on these. So these could be like reflective surfaces, optical or acoustic. This out. All right, let's get these off here. so you guys got a paper in front of you, right? You guys got paper? Okay. So put your name on your paper. Name. Everybody just write your name on your paper. Right? I'm gonna have you guys turn this in at the end of class. So when you turn this in at the end of class, as long as you do, we're gonna do 6 diagrams, right? As long as you have all 6 and they all look good, check out, then you'll get points in the book. I'm gonna title this Ray Diagrams dash reflection. Right? We're gonna save refraction and Snell's law for another day. So we're not talking about prisms or anything like that. Today we're talking about all about mirrors. Today's all about mirrors and reflection. Okay. So you guys got your name. You guys got ray diagrams, reflection. Okay. You should have a ruler. You guys got a ruler. If you don't, for whatever reason, see some on some empty desks. Okay. Say about halfway down the page, maybe a little bit, tiny bit below that. We're going to dash off a horizontal line. We're going to do 3 dashed horizontal lines. Right. So you got one just below, halfway down. Okay. Okay. Go about a quarter way down below that. Dash off a horizontal line, or it's the width of the paper. Okay. And then about a quarter of the way up from that line, do a dash line. So you got these 3 dashed lines. Okay. That's going to be 3 of the scenarios. And then on the back side of the paper, we'll do another 3. Okay. So well, by the end of class, you'll have 6 diagrams altogether. Okay. Okay. There's going to be 3 of those diagrams. Okay. So let's start with some convex mirrors. Convex mirrors. Okay. So I'm going to draw a. How about let's do a really tightly curved convex mirror right here. Right. Then I'll do one that's we'll say it's just like flatter. Right. So it's not as curved. Okay. And this third one, I'll make almost a plane. I'm going to scoot it kind of far to the left. So what if it has just a little bit of curvature, but hardly anything? It's almost a plane at this point. Okay, guys, that. So it starts off really tightly curved, and then less curved, and then it's getting pretty close to flat. Right. Okay. Now, remember how we're sort of defining how curved is something is with the focal point and the focal distance. So hand in hand with that, maybe if it's really curved, that's like this could be like this is part of a large spherical surface. This might be the center of the circle, and halfway from the surface to that point is the focal point. So I'm going to put a focal point right about there. Call it F for focal point. Right? F for focal point. Okay. And then as it gets less and less curved, that focal point's moving further and further away. So maybe the second one, maybe the focal point's like over here, for example. F for focal point. Okay. And then this third example, when it's getting pretty close to a plane, well, guys, if it was a true plane mirror, how far away would the focal point be? Here. Oh, let's go back to this one, right? Right. Can you guys imagine? Remember this sphere that's a mirrored surface, this reflective surface mirror sphere, right? What if we make this bigger, bigger, bigger? What if I blow it up to like the size of the Earth? Right? If you were standing right in front of that, at that point would it pretty much look like a plane, right? You might think it was flat, right? If you're standing on the surface of Earth, if you're just kind of looking around you, if you're like some like caveman 50,000 years ago, it's kind of hard to tell that the Earth like isn't flat, right? So, just the reverse of that is that if you do have a plane mirror, this focal distance becomes infinitely far away, right? So, well, I can't quite do that on this paper, but maybe the closest I could get is I can put the focal point on the opposite side of the paper. So I'm going to put it way over there. There's my focal point. Okay. Right. So we're going to watch a progression of what happens to this guy's reflection. Well, I need an object. Okay. Paul Hewitt was using candles yesterday. I'm going to use a stick figure. So let's have a stick figure. Let's start him off over here. Right. I'm going to call this object. Right. And then if the mirrored surface is less curved, that kind of goes hand in hand with like taking this could be the backside of a spoon. What if you just move that spoon further away from your face? Okay. Or hold on. Sorry, I'm getting this backwards. Let's say closer to your face. Closer to your face. Right. So let's get the object in here. Okay. object, right? Kind of like you move the spoon closer to your face, right? That's going to go hand in hand with saying like the distance from the object to the surface is proportionally smaller compared to this focal distance, the distance from the surface to the focal point. Okay, so maybe I should label that too, right? Like the distance from the surface to the focal point is called the focal distance. Focal distance. Right. And in the equation, I'm going to just call that F. Okay. So from the first picture to the second picture, if you imagine sort of an animation, right? Get some proportional change that could describe one of two stories. Either you're getting your face closer to the backside of the spoon, or the mirror is becoming less curvy. Right? The stories kind of go hand in hand. Okay. And this third one, let's put this guy in front of a mirror that's almost a plane mirror at that point. Okay. So object. All right. So just glance around the room. Okay, yeah. Looks like you guys got these so far. You guys keeping up with me? Looks like. All right, everybody keeping up with me. We good? Okay. So now remember, these are all mirrored surfaces. I might even write that. I might write this as a convex mirror. You don't have to write that if you don't want. It's kind of taken care of with the title says reflection. Okay? We're going to do ray diagrams, and then we're going to break up that algebra equation and see if that aligns with the ray diagrams, right? To figure out where is the image, where's reflection going to be. Right? Right, you guys ready to draw ray diagrams? Okay. Now I'm going to switch to pink ink. If you're still using the same color, that's okay. But I'm going to use the pink ink to draw light rays. Right now, if there's a light on the sky, I bet there's like a bajillion different light rays heading all crazy different directions, scattered all different directions. Right? But I only need to follow a couple of rays to figure out where his reflection is going to be. Okay. The first ray, let's skirt across the top of his head, parallel to the ground. Across the top of his head, parallel to the ground. Take that all the way to the mirrored surface. Right? You guys got that first light ray, parallel to the ground, across the top of his head. Take that all the way to the mirrored surface. Okay? And that's going to reflect off. Guys, is that going to bounce straight back? No, because it's not a flat mirror. Is that going to bounce off kind of up to the leftish?
Yeah.
Yeah. But how do you know exactly which direction up to left to draw? Because it would align with the focal point. Notice I'm drawing here from this point. See how my rulers align with the focal point? Guys, see it? Okay. So it's going to bounce off, boing, that direction. Okay. Now, before you move your ruler, go ahead and extrapolate backwards. Because if you're out in the real world, it looks like this light ray came back from this direction. And I'm dashing this bit right here. It looks like it came back from that way. Right? Although there's no light that actually crosses the mirrored surface, but it looks like it came from that way. Right? And that light ray could go both ways. So if it was like a laser light going parallel to the ground, it would bounce off that direction. But if it came from that direction, it would bounce off and going back parallel to the ground. Right? Which is kind of a hint as to the next ray we're going to do. Let's go back to the top of his head. Okay, back to the top of his head. And we're going to draw a ray headed straight towards that focal point. What if there's a ray of light going in this direction? Okay. Now, of course, it doesn't actually cross the mirrored surface. If you want to, you could dash, say, well, let's kind of head off that direction. Okay. Okay. But it's going to bounce off the mirror, and guess which way it's going to bounce? Boing, back parallel to the ground, Okay. And if you're out in the real world, you're going to say, well, it looks like it came from back in this direction. So go ahead and extrapolate back towards the right. Go ahead, dash that. Right? All my dash lines are like, looks like the rays are coming from that direction. Right? And oh, look at where those dashed extrapolations cross. Right there. So that will be the top of his head for the reflection. I'm going to draw the top of his head there. Okay. And then I could do the whole same process for his feet. But notice his feet are on the floor that I have also going through the focal point. So his feet are going to end up also on the ground. So my image, I'll do exactly that. You guys see a little tiny stick figure I just drew? A little tiny stick figure? Where those rays cross the top of his head for the reflection. And his feet are also on this dashed line ground. Right? And this is an image. And the fact that it's on the opposite side, I'll call this a virtual image. Virtual image. Right? Virtual just means it looks like it's on the opposite side of the mirror, just like a regular mirror. Right? you look in a plane mirror, it also creates a virtual image. Okay. Okay. You guys got that? Okay. Okay. Now, second scenario. Oh no, sorry. But before I go on, okay, let's do some math. Now, as long as you're kind of like mine, then that's all right. Right. I'm gonna get some exact measurements. Your measurements don't have to be exactly mine. That's all right. Okay. That's probably kind of close, right? So it looks like the object I have them drawn about looks like 6.8 centimeters from the surface. The focal distance looks like we'll call it 3.3 centimeters, somewhere thereabouts. Okay. Let's break out that algebra equation and see where does that say the image should land, and then we'll think. Right. So 1 over focal length equals 1 over distance object plus 1 over distance image. Right. Let's say I'm solving for a distance image given those first two measurements. So I said the focal length was like 3.3 centimeters, and the fact it's on the opposite side, I'll call it negative. So 1 over negative 3.3 centimeters equals, right? Now the object I'm going to define is always on the positive side, right? And I measured that as being 6.8 centimeters. So 6.8 centimeters. Right. Now let's see, where does the math say that the image should land? Right? And then we'll go measure and see how close that is. Right? So calculator, I'm going to take this fraction, subtract it over. So 1 over negative 3.3 minus 1 over 6.8. Right? Go ahead and throw in the middle step here, negative 0.450 something, right? Equals 1 over di. Right? Right. Now, guys, if you get that far, what's the next math step? What do you have to do to both sides? Take their reciprocal. Right? Reciprocal. Right? So I could do two ways. I could do 1 over the answer, or I could hit this key above the 7 that says x to the minus 1. Both ways will do it. So 1 over the answer is a way to do it. Okay. Meaning distance image is negative 2.22 centimeters. Okay. That's what the math says where the image should show up, the reflection. Right? Okay. The fact that it's negative means it'll be a virtual image. It'll be on the opposite side. It says about 2.2 centimeters, right? Let's see what the ray diagram said. Where did the image actually land? Okay. Ooh, look at that. So I'm going to call it about 2.4 centimeters. All right. So the math says 2.2 centimeters. My measurements from the ray diagram show about 2.4 centimeters. Yeah, that's a near match. Right? You guys get it? Right. Now, next one. So if you're saying what happened from the first one and second one, you could attach one of two different stories. Either the mirror got flatter or you moved your face closer. One or the other kind of handles both. Right. So let's do ray diagrams. Right. And again, there's a bajillion rays bouncing off the sky, but we only need to follow 2 rays to get the answer as to where's the reflection. You're going to start off 1 ray parallel to the ground, skirting across the top of his head. Right there. Right. Yeah, that's going to bounce off up to the left. And notice I aligned my ruler with the focal point. You guys see my ruler's aligned with the focal point? Okay. It's going to bounce off, going that way right there. Okay. But before I remove my ruler, I'm going to extrapolate backwards. It looks like that ray of light came from back this way. Boing, boing, boing. Yeah. Okay. Everybody got that so far? You guys keep it up with me. Right, then let's go for the top of his head straight toward the focal point. Right, top of his head straight toward the focal point. Right. Right. Now, of course, this ray light, this ray light won't cross the mirrored surface. So it's headed straight towards, right? But it's going to bounce off right here, boing, boing, back parallel to the ground. Right. And again, before you move your ruler, go ahead and extrapolate back to the right. It looks like that ray light came from this direction right here. Right, that big? Right. And oh, look where those 2 extrapolated rays cross behind the mirrored surface. Yeah, that's going to be the top of his head for the reflection. We'll go ahead and put his feet on the ground. If you do that whole process for his feet, they would just show up on the ground. Okay. Ooh, it looks a little bit bigger.
My bad.
So this is another virtual image. Virtual image. Great. Oh yeah.
Sorry, how did you get this? Okay.
Yeah. So let's go that process again. Right. So all right. So go back to the beginning. The first line I drew, the first ray, I did across the top of his head, parallel to the ground. Then I'm gonna bounce that off. Align my ruler with this focal point, bounces that way, and extrapolate backwards. Okay. Then I went back to the top of his head and aim a ray of light straight toward the focal point. Okay. Now that's gonna bounce off the mirrored surface right here, back parallel to the ground, and extrapolate that backwards. Okay. That's and where those extrapolations cross, that's where the image is. Okay. All right. So while you guys are finished with that one, let me bring up this this mirror equation again. Let's see how close this is. 1 over focal distance equals 1 over distance object plus 1 over distance image. Okay. I'll do the same thing I did before. I'll go ahead and solve for distance image and see where it shows up. So my object, I've got, I'll call it 3.9 centimeters. So 3.9 centimeters right there, distance object. Right. I'll always call a distance object positive. That way. Right. So my focal point looks like it's on the negative side. That's 8 centimeters exactly, 8.0 centimeters. And it's on the opposite side, so I'll call it negative 8.0 centimeters. Right there. Okay. Let's say I'm solving for distance image. Where should the image show up? Okay. So same as before, 1 over negative 8 minus 1 over 3.9. Then take the reciprocal. I'll use that key above the 7, the x negative 1 key, take the reciprocal. Okay. I'm getting distance image is negative 2.62 centimeters. Okay. Probably a bit too much precision. So maybe about negative 2.6 centimeters, negative 2.5 centimeters, somewhere. Okay. So let's see, where did my image show up according to my ray diagram? I hope it's at the same location. Let's see how close that is. So, that's about negative 2.8 centimeters. Yeah, about negative 2.8. So the algebra equation says negative 2.6 centimeter. Right? My ray diagram shows it as negative 2.8 centimeters. So yeah, that's like a near match. Yeah, we're doing good so far. Right? Yeah, if you're trying this on yours, your numbers might be slightly different. That's okay. All right. You guys ready for the third one? Okay. Remember, the idea of the third one is that this is getting close to approximating a plane mirror at this point. It's not quite a plane. It still is a little bit convex. Okay. But yeah, everyday experience with a plane mirror, you should show up about on the opposite side, about equal height. So let's see if the ray diagram is consistent with that. Okay. So same method we've been doing all along. Just follow a couple of rays of light. The first ray of light, let's go across the top of his head, parallel to the ground. That's going to intercept this mirrored surface, bam, right there. Right. And then it doesn't reflect exactly straight back because it's not exactly a plane. But if you just turn your ruler a few degrees, then it'll lock in with that focal point. That's boing, the direction that ray reflects back. Right. Almost parallel to the ground. Right. And then before you move your ruler, go ahead and extrapolate backwards, straight toward that focal point. Say, it looks like that ray came from that direction. Right. All right, there's good. Okay, so that's the first ray. Boing. Now let's do the next ray to figure out where is his image going to be. I'm going to go from the top of his head straight toward the focal point. Just like we did for the first two diagrams. Top of his head straight toward the focal point. So it looks like it came from this direction. Okay. All right. But where it's would be crossing the mirror, of course, it doesn't actually cross. Right. It's going to reflect back parallel to the ground. Back parallel to the ground. Point. Right. And then before you move your ruler, extrapolate back into the paper. Say, well, it looks like it came from that direction right there. So that would be. Okay. Oh, and look where those extrapolated rays cross. Because that right there is where the image is going to be. Okay. It's still a virtual image. because he looks like he's on the opposite side. Right. So the first three ray diagrams we did, we got kind of similar results. They're all virtual images. Right? They're all virtual images. Right. Let's do the math for an actual plane mirror. So I'll go ahead and call this plane mirror for the math. 1 over f equals 1 over distance object plus 1 over distance image. Okay. Let's say the same as before. Say we solve for that. Right. So my object, let's have this guy. Let's see, my diagram shown, call it 3.7 centimeters. Right. So 3.7 centimeters right there. So that's this number right here. So 1 over that, 3.7 centimeters. Say I'm solving for a distance image and equals 1 over, okay. See how many guys get this. See if anybody gets this. If I'm talking about a true plane mirror, a flat plane mirror, mathematically, what number should I plug in for the focal distance? Infinity. Yes, right. I'm also going to tag a negative sign onto it, but it's not going to make a difference in the end. So I'll call it negative infinity centimeters, something like that. Okay. Yeah, the idea, again, is that if you have a, here, if I have this diagram, right? If you're trying to figure out, well, how am I doing infinity, right? So you had a mirror ball, and you just blew this up bigger, until it's like the size of the Earth, right? Well, this radius and then this focal point would just be crazy far off to the right, right? And you can keep going bigger, but like the size of Jupiter, the size of the sun, right? Somewhat, size of the observable universe, right? It's going to approach infinity, and so the surface would approach a plane, right? It would look like a plane. Okay. So, right, right. Now the next question then is, what is 1 over that? Guys, what is 1 over infinity?
No.
Zero. Guys, that's a good thing you know before you graduate high school. I'll tell you one reason why. Let's say a few years from now, you go buy a lottery ticket and you have a 1 in 20 million chance of winning. Guys, 1 in 20 million. Okay, so for all practical purposes, what's your chance of winning the lottery? 0, right? Try the calculator. What is 1 over 20 million? 0.000. It's like a string of zeros before it hits it. Yeah. So it's getting closer to 0. I'm going to call it 0. Well, negative, whatever. It's still 0. Right. So now I could finish off the math, but if you stand back and look at this big picture, you probably see by symmetry what the answer is going to be. Guys, what's the answer by symmetry? Is it negative 3.7 centimeters? Right. So the negative means it's virtual. The image is on the opposite side. Right. And oh, look, it's the same magnitude. Look at that. So it's like equal distance for a plane mirror. Right? Ray diagram looks about the same. You guys get there? Oh, yeah. Oh, yes, yeah. All right, you guys good? All right, now let's switch over and do some concave mirrors. Okay. All right, so on the back side of paper, we're going to dash off also 3 lines. We're going to do 3 diagrams right here. Right through the center right there. All right, go about a quarter of the way up, dash off a ground. And about a quarter way down, dash off a ground. Okay. Got these 3 dashed lines. Right, you guys got also 3 dashed lines? 3 dashed lines? 3 dashed lines. Oh, so we're gonna do concave mirrors. Let's do let's have the first one kind of tightly curved. And the second one, maybe not as curved, but still kind of curved. Okay. Okay. And maybe the third one, I'll do kind of similar to the second one. Okay, something like that. Okay, so three mirrors, right? And I'm gonna call these concave mirrors. Okay. The way I always remember is it concave or convex, right? Like a cave opens up like there's a hole, right? So if I'm looking from the left to the right, right? Oh, it opens up like a cave, hence concave. Okay. I need to define some focal points. So this first one, put the focal point right here. Second one, focal point right about here. And the third one, let's put it, say way back here. Yeah. Okay. Right. Now, if we're talking about concave mirrors, I've got a couple of examples just within radian distance here. So here's a cosmetic mirror. Well, one side is plain, and the other side has a little bit of concavity to it. It's a little bit concave. Okay? Well, guys, isn't the purpose of a concave mirror that if you hold it close to your face, it'll blow up your image larger? Okay? So hold on to that idea, because we're going to see that later. Okay? Also, I got this this UFO pig. Right? If I take this apart, it's a couple of concave mirrors, right? Put the top on. If you're standing at the right angle, then it looks like there's a pig here that you can pick up, but he's not really there. Right? It's just an illusion, right? I'm going to pass this around. And guys, when I pass this around, go ahead see the illusion itself, but take this apart and hold this close to your face and far away from your face. Because these ray diagrams we're going to do, we're going to do 3 different stories. They're going to show up really different outcomes depending on where's the object compared to the focal point. Okay? So the first picture, I'm going to put the object outside the focal length. I'll put them more than twice as far out. Right. The second one, I'm going to put him right on top of the focal point. Ooh, that'll be an interesting one. Right. And this third one, let's put him pretty close to the surface compared to the focal length. Right. So object, object, object. Right. And if that's an object in front of a mirrored surface, you could think of that being like your eyeball, right? So there's your eyeball. You look in front. It's like in front of a cosmetic mirror. So this first one is if you hold the cosmetic mirror really far away from your face, right? So that your eyeball is outside the focal distance. Right? Or you can think, what if you have a really tightly curved spoon? Right? Those two stories kind of go hand in hand, right? Let's see where's the image going to be. Right? Let's use the exact same method we used for the convex mirrors. Now they're concave. Right? Start off with the ray of light, skirting across the top of his head, parallel to the ground. There's one ray of light right there. Boom. Okay. That's going to bounce off. Guys, which way is that going to bounce off? Right through the focal point. Ba-boing. That's it. Ba-boing. All right, everybody just draw a ba-boing. Now let's go back to the top of his head, straight toward the focal point. And that's going to bounce off, ba-boing, parallel to the ground. And you guys see where those rays cross? Right? That's going to be the top of his head, except now he's going to be upside down. His feet are still going to be on the ground. So now I have an inverted image. You guys see inverted image? I call that. And also it's hovering in front of the mirror. Ooh. So not only is it inverted, it's a real image. That's an inverted real image. Inverted because it's upside down. Real because it looks like it's on the same side as the object. It looks like it's hovering in front of the mirror. Hey, kind of like that pink pig. Right? It was a real image. Real as opposed to virtual. Virtual looks like it's on the opposite side. The first 3 we did raw. Virtual looks like they're on the opposite side. Right? Plane mirror is virtual. Right? But this concave mirror, if you're standing kind of far away from it, or it's curved a significant amount, might create a real image. Ooh, it's hovering in front of it. Okay. You guys got that one? While you guys are finished in that, see some of you guys still working on that. Let me try out the map. So my object is 9.0 centimeters away, 9.0 centimeters. This focal distance is 3.0 centimeters. Okay, so let's try the math with that. So let's go 1 over focal distance is 1 over distance object plus 1 over distance image. Let's solve for distance image. Okay. So I have 3 centimeters is my focal length. Okay. And 9 centimeters is the object distance. Okay. Those are both positive values because they're both on the same side as the object, both on the positive side. Okay. plus 1 over distance image. Let's say where should the image show up? Okay, and then we'll go measure it and see if it's a match. So 1 over 3 minus 1 over 9, subtract that over, and then take the reciprocal. I'm getting distance image is positive 4.5 centimeters from the surface. Positive 4.5 centimeters from the surface. Okay. Let's see how close it landed on my diagram. So go from the image to the surface. Oh, look at that, 4.4 centimeters. So my ray diagram is showing 4.4 centimeters, and the math says it should have been 4.5 centimeters. That's pretty well a match too, isn't it? Yeah, yeah. Right. So I've got 2 different ways to find out where's the image going to be. The ray diagram and algebra equation. Okay. All right, you guys good so far? Good so far? Okay. All right. I'm gonna skip the second one and come back to it. No, I drew it in this order because there's kind of like a logical progression, but we're gonna do this last one next. Right? So same method as we've been doing all along. Let's have a ray of light going parallel to the ground, skirting across the top of his head. That's gonna hit this mirrored surface and boing, bounce off through the focal point. Right? Then before you move your ruler, go ahead and extrapolate backwards behind the mirror, because this one's going to be another virtual image. Right? Which you might have guessed this one's going to be a virtual image, because if you use a cosmetic mirror, you know, should blow up your image bigger. But let's see if that's also true. Okay. Now let's go from the top of his head through the focal point. Now this one you might have to extend your mirror. You guys see if I line the focal point with the top of his head? Well, I guess it barely touches the top of our mirror, but if it doesn't, you might have to extend your mirror. Okay, right? You might have to extend your mirror for what we're about to do right here. From the focal point to the top of his head. Right? Okay. And that's gonna boing, reflect back parallel to the ground. Also parallel to the first ray. About like that. Okay. Go ahead and extrapolate that one back behind the mirror. For your ruler. Like that. Right? Right. Oh, and see where those 2 extrapolated rays cross? That's the top of his head in the reflected world. Okay. Gotta draw his feet still on the ground, because that would still work out that way. Right. Now we're back to a virtual image. Okay. Now, if you guys are taking, I'm passing around that UFO pic, see it back there. Right? If you guys take the parts apart, right, and move one of those parabolic mirrors really close to your face, you should see a blown up image, kind of like this cosmetic mirror. Okay? And if you hold it really far away from your face, you should see an inverted image. You should turn upside down, right? But what if you hold it again, like closer, further away, closer, further away? What if you put a distance from your face so that your eyeball is right on top of the focal point of that parabolic mirror itself? Okay. What does that look like? What is like halfway between this situation and this situation? Well, let's find out with ray diagram. Okay. So I forgot to do the math on this. Well, okay, here, we'll do the ray diagram first, and I'll go back and do the math on these last 2. So ray diagram, let's do a ray parallel to the ground, and then bounces through the focal point, boing like that. And then we'll go from the top of his head through the focal point. But, ooh, it's not going to be pretty well a vertical line, pretty close to vertical. So it's never going to cross the mirror. Now what? How do you even interpret that? Right? What do you guys see? Who has the UFO pig right now? Right.
I do.
Okay, as you move it closer and further away, if you take it apart, take apart the 2 halves, move it closer and further away. At some point, you're going to flip from upside down to right side up. What's right in the middle? I bet you see just a giant blur of light. Do you see just a giant blur of light? And we're going to call that no image. No image. Right? There'll be no discernible image. Okay. Now let's do the math on these last 2. So right, do the math on this one. So I'll do that one first. 1 over F is 1 over DO plus 1 over DI. Right. Now this focal length is 12.1 centimeters. I've got, because 1 over 12.1 centimeters equals 1 over, my object is 3.2 about 3.2 centimeters. 3.2 centimeters. Okay, let's see where the math says the image should have been. Okay. Hopefully I get a negative number because I'm seeing a virtual image show up in my ray diagram. So let's do 1 over 12.1 minus 1 over 3.2 equals, okay, some negative decimal. Then take the reciprocal. I'm getting distance image is negative 4.35 centimeters. Okay. Let's see how close the math got it. Negative 4 point something centimeters. Okay. My ray diagram. Oh, well, okay. It looks like that one's off a little bit. My ray diagram's showing some maybe about from this point, maybe about like 3 centimeters or so. Okay. But it got it on the correct side. Right? It's negative. Right? And I guess not too far off. Right? 3 versus 4 centimeters, pretty close. Right? Okay. And finally, what about the math for the one where it blows up in no image? 1 over f is 1 over do plus 1 over di. Okay. Now this one, the object and the focal point are the same distance. And I'm showing what 6.5 centimeters looks like. So 1 over 6.5 centimeters equals 1 over 6.5 centimeters plus 1 over di. Right? Subtract this over, it zeroes out. Guys, mathematically, what's the answer to this equation? 1 over what is equal to 0?
Infinity.
Infinity. Infinity. Right? It could be plus or minus infinity. Right? Yeah. So it's gonna. That's the math that aligns with there being no image at all. You just see a blur. Okay. Right, you guys good there? All right. All right. So when you finish those ray diagrams, go ahead, turn those into the gray tray. And I got a Vsauce on mirrors to round out the class.